applying Newton's laws of motion, F equals ma, to various situations. So one of the situations, the last one we looked at, was dragging a block by applying a force, we call it F here, and dragging it to the right. And the question was doing this with friction and without friction. We did it without friction, and we started doing it with friction, as I have here. And the approach was to draw all the forces acting on this object. There's an object in question, which is this mass. And what are the forces acting on it? The forces acting on it are the three red ones in red. Normal force up, the weight down, the force you're dragging it with, which is F. And if this friction is a force of friction opposing the motion, so it's kinetic friction. So we were trying to answer these questions. First of all, what is the normal force and what is the acceleration? So to find the normal force, basically we apply this Newton's second law to all the forces in the y direction. In the y direction, this the normal force, and there's the force of the weight here. But also this force F here has two components. It's got an upward component and it's got a horizontal component here. So there is another force here in the y direction, than this one here. And it is, if you look at this angle here, it's F, which is 10 in this case, times the sine of this angle. So that's 5 newtons up. So I'll put the 5 over here. The x component of this force is F, which is 10 times cosine of this angle. And so that is 8.66. So now applying this, all the forces up to answer the first question. We did this last time, I'm just reviewing. To answer the first question, what is the normal force? Okay. So all the forces in the y direction is 2 up. And 5, those 2 are up. And there's 1 down. And what this tells you is that the normal force is no longer equal to the weight. It's less than the weight. Okay, now we're going to need the normal force to answer the second part of the question. What is the acceleration? So the acceleration, we're going to apply Newton's laws in the x direction. Okay, in other words, the sum of the forces in the y direction equals 0 because there's no motion up or down. Nothing's moving up and down. But in the x direction, yes, things are moving to the right. And so what are the forces? Well, we can see this component, 8.66 Fx. So we're going to write that 8.66 minus the force of friction. And that's kinetic friction. And that is equal to ma, which is what we're looking for, the acceleration here. Now, when there's no friction, we can just solve this equation for 8.66, where the mass is 2. So I could have just put in 2 over here. All right. But since there is force of friction, the force of friction is equal to mu, which in this case is 0.2, times the normal force, which is this. All right. It's going to mg minus 5. M, 2 times 10 minus 5 is 15. So the normal force is 15. All right. Or if you use 9.8, then it's 14.6, not 15. All right. So mu times the normal force. I'm using 9.8 over here. So the force of friction is 2.92. So now we can apply this equation to figure out what A is. And it's 8.66 minus Fk, which is 2.92, and that's equal to Ma, equal to 2A. And you saw this equation for A, and the answer was over here, 2.87. So this is the equation that I just wrote here. A comes out to 2.87 meters per second per second. So that's the last thing we did last time. And then we actually went on to study the a body sitting on an inclined plane. So if an object is just sitting on a table, let's say, these are the forces acting on it. Now, if you tilt the table, what are the forces acting on it? Well, weight is still down. Weight is not at an angle. So basically, I had asked you last time, which of these is the right diagram for the forces? And basically, E was the right diagram. The normal force is this way. The weight is still down, and the friction force is against the motion. You can see it a little bit better over here. Okay. This is not here right now. Okay. So these are the force diagram for an object sitting on an inclined plane. So then we started analyzing that problem. So let's draw the forces again. This is the normal force. Right, this is the normal force. This is the weight. It's always straight down. And this would be the force of friction. If this is moving down the plane, the force of friction is up. If it would happen to be moving up the plane, then the force of friction would be down. In other words, if you gave it a push and it was going up and slowing down, then the force of friction would be down. Okay. So one of the things, so how do we analyze this? And we saw that one of the things that made life a little simple is to draw the x-axis. Yeah, draw the x and the y-axis at an angle, like I did here. Okay, and the reason for doing that is because there's no motion along one of the directions, along the y-axis. If you assume this is the y-axis, there's no motion up or down. Things are just moving left and right over here along the plane. But all the forces that we had are still the same. They're still here. Okay. And again, if it's moving down the plane, those are the forces. So now we were trying to apply Newton's laws. This is where we left off last time. First of all, in the y direction. See, this is why we drew the axis at an angle, because we can say this now. All the forces in the y direction, the sum of them equals 0, because there's no motion up or down. What are the forces in the y direction? Well, we know this is the normal force. All right. This is the weight down here. That's it, along the y direction. What are all the forces in the x direction? Well, in the x direction, all the forces are not equal to 0 anymore. There's motion, the thing is sliding down. So there's some acceleration. And there is one of the forces in the x direction is in fact the force of friction, which I have over here. This force of friction is equal to mu n. Okay, we'll put that in later. Right now, let me just write it down. Now let's do this first. Since this force here, the weight, is not along any of the axes, we have to resolve it into components. In other words, it's got a y component and an x component. It's a little too long. Both of these are a little too long. Okay. Now, this x component, this distance here, is opposite this angle. So that's going to be mg sine of theta. The green one here, mg, this is going to be, it's adjacent to theta, so that's going to be mg cosine theta. So we're going to give some numbers here. The numbers, I think, should be listed here. What are they? Where did I put the numbers here? Here we are. Okay, a 10 kilogram mass at a 30-degree angle. What is acceleration? What is the normal force? All right. So again, these are the forces as we left them off over here, and this is without friction, and which we did the previous class. And with friction, this looks like this. Okay, there's a force here. So again, all the forces in the y direction told us this, that n is equal to mg cosine of 30, and therefore, if you put in the values for m in this case, you get that. And this is what's given. I should have just copied it. Okay. So the mass is given. If you put in the mass, 10 kilograms, angle 30, you get 86.6 Newton is the normal force. Now, if you do part 2 here, we have up the plane, we have the frictional force. Down the plane, we have mg sine theta. So this one minus that one, mg sine theta, minus the frictional force, equals ma. If it's going down with constant speed, then it's 0. But if it's not going down with constant speed, it is not 0. It's equal to ma. So let me show you what I'm talking about here, because first of all, I want to go with constant speed. And I think you did this in your lab. Maybe you didn't, but this is usually the experiment the students do over here. So here's the mass on the inclined plane. You can see this little arrow here. That's the force of friction. And one way to find the force of friction is to increase this angle a little bit at a time until this thing starts sliding down with constant speed. And if you know the angle, you can figure out very easily the coefficient of friction, what we call mu. All right, because you were wondering probably how do you find mu? Well, this is one way. So let me do that. So let me increase the angle. I'll play this. So I play this now. See, it's set at 10, but it's not sliding because the force down is not big enough to overcome the force of static friction. So let me increase the angle a little bit at a time. And you notice right now at 21 degrees, it started sliding. I stopped it here. I'm going to let it go a little bit more. It started sliding and more or less at constant speed, as you can see. Constant speed. Obviously slowing down. So as the angle was 21 degrees, now we don't forget, when he's pushing it up, the force of friction is against against them. Let's play that one more time. Because you can record what you did. This was me before playing with this. Okay, so basically I'm going to be increasing, beginning just about now, I'll be increasing the angle to find at what angle does it start. There we go, 21 degrees. He's going to run over the guy here, yes. So the guy's mad, he's going to push it back up. And he's going to let it go. But don't forget, once it's going up, you notice the force of friction was opposite, was down the plane. So the fact that we find the angle at which it moves at constant speed down the plane, from that you can figure out, and I'll show you how, you can figure out what the coefficient of friction is. So let's assume this is exactly what happens. It's not standing, it is moving, but it's not accelerating. It's moving down at constant speed. You increase that angle until it starts moving down. That means all the forces add up to 0. All right, or that means the force of static friction. Don't forget, this is the angle at which it started moving, is equal to mu times the normal force. The normal force is equal to mg cosine theta, or 86.6. All right, but right now I'm not going to put any numbers in yet. Okay. Okay, let me go to the next slide here. Well, I guess I did put in numbers. All right. I guess I should go and finish up the problem I was doing. Hold on. Let me go on. So to the situation where the speed is constant again. So we just saw that when the speed is constant, the force of static friction is mu mg cosine theta, and the normal force is mg sine theta. So both of those have to add up to 0, and I'm going to put in for F this. So don't forget, this is what I'm writing. This is the normal force. This is the force of friction, and both of those are 0 because there's no acceleration. We're just using that angle, so it just starts moving at constant speed. All right. So for F, I'm going to put in mu mg cosine theta. Now, an interesting thing happens. I'll do it in red. If I bring this on the other side, which I think is what I do here. Oh, not yet. If I bring this on the other side, mg here cancels mg here. So I'm going to solve this equation for mu. Mu cosine theta, that's all that's left here, is equal to the left side of the equation, which is sine theta. Now I'm going to solve this for mu. Is equal to sine theta divided by tangent theta. I'm sorry, divided by cosine theta, which is tangent theta. This whole thing is tangent theta. Sine over cosine, if you remember from trig, is tangent. So basically, to find mu, all we got to do is find the tangent of the angle which you just started slipping, which remember was about 21 degrees. So I'm using my calculator to find the tangent of 21 degrees, and it's 0.38. So again, if you find the angle at which this just moves down with constant speed, doesn't accelerate approximately, that the tangent of that angle, whatever that angle is in fact the coefficient of friction. Okay, now if it accelerates down, well, then things are a little bit different. You can find what that acceleration is. It accelerates down at some angle here. And again, the angle now says 30 instead of 21. Forget 21, it just started moving, but so 30 is going to accelerate down. What's going to be the force of friction? Well, and we're putting in friction over here, depending what mu is. For example, let's say mu is 0.1. So the force of friction is going to be mu mg cosine theta, mu is 0.1. And here's the calculations to find the normal force, 8.66. And here's the calculations to find the acceleration, right? It's this 8.66 up, and this is 50 down. It's mg sine theta, right? Mg sine theta. So for these numbers, that comes out to 50. And the difference between those two, 50 minus this, right? Mg sine theta, which is 50, minus 8.66, which is Fs, is equal to Ma, which is 10A. And you can solve for A here to be 4.13 meters per second per second. Don't forget, this comes from mu times the normal force over here. And this is mg sine theta. And the difference between those two, this is equal to Ma. So there's one more example I'd like to do. And I have a simulation that goes with this. This is called the Atwood machine. And it looks like this. An Atwood machine is a pulley, and you have two masses on each side. If the masses are not the same, then if you let this go, this will start accelerating down. All right, now I'm going to show that to you in a little simulation in a minute. But this is what I'm going to come back to this in a second. But say this mass on the right is heavier, M2. This is M2. This is M1. So these are the forces acting on it. There's a weight, and there's a tension in the string, right? There's a string holding it. The string goes over the pulley, so the tension here is the same as the tension here. If I'm going to call this T, I call this T also, but it's a different weight here. So let me show you the simulation. My flash player. This is the next topic. Let me go to. I think this is it. Yep. Nope. One more. This is it. All right. So this mass here, these masses said 16 kilograms in this example. M2 is 16. M1 is 12. So this is bigger. So what's going to happen is this is going to go up, accelerate. It will accelerate up, and this will accelerate down. And basically here are the answers to some of the questions, which is going to be what's the acceleration? You can see the answer here, but we're going to try to figure out how to figure this out. And what's the tension in the string, which is this. But first of all, let's just do the simulation. So you notice what happens. This is accelerating up. This is accelerating down at the same rate. This is A, this is A. Also, this is T, then this is T also. Okay. So let's see how you come up with these numbers. And in this simulation, you can change the masses here if you want. So again, what we're going to do is we're going to isolate each mass. We're going to look at one mass, apply F equals ma, then look at the other one, apply F equals ma by itself. So the mass on the left, these are the forces. So T, the sum of the forces, T is positive, M1G is negative. So the sum of the forces is T minus M1G equals M1A. Okay. How about this side? This is the same thing. T minus M2G equals M2A, but A here is negative because it's down. See, it's negative. So this is the equation. So we're going to solve for T here and solve for T here. If I solve for T here, I bring this on the other side, M2G. I have minus M2A plus M2G. If I solve for T here, I get M1G plus M1A. And this T is the same as this one, so I'm going to let this equal that in the next slide. I have it over here. One equation gives you T this, the other equation gives you T that. So I let this equals that. So basically what I'm going to do is erase this, and this is T also. This equals that. And I'm going to solve this equation for A. It means I'm going to bring everything that's got A on one side of the equation. Okay. So, so I'm going to bring I have M2A minus M2A let's do it the other way around. Let's bring this on this side of the equation. So on the right side, I'll have, that's where I'm starting to write, I'll have M2A plus M1A. And on the left side, I'm going to bring M2G. I'm going to bring this on the other side. That'll be M1G plus M2G. If I didn't make a mistake here, which I may have, I have the solution here. So so you can factor out an A here. A times M2 plus M1 or M1 plus M2. And here you factor out a G on the left side of M2 minus M1. And then divide both sides by, I'll make that a different color. Divide both sides by M1 plus M2. And same thing, this side divide by M1 plus M2. And lo and behold, You have this equation here. The acceleration is g times the, even though this is complicated, look at the equation. G times the difference in the weights divided by the sum of the weights. Very simple. Right? These weights are different. So it's going to be g times the difference in the masses divided by the sum of the masses. And if you put that in for this number, what's A? Let's put it in. We know what the answer is from the simulation. If I remember, it's 1.4 something, right? So what's G? Well, it's 9.8. What's M1 minus M2? Remember, this was 16, this was 12. So M1 minus M2 is 4. What's M1 plus M2? Well, 12 plus 16, it's 28. And lo and behold, you get, I think, 1.47 meters per second squared. Here it is. 1.4 meters per second squared. And of course, you can, just to check that, you can change these numbers. Let's say make this 15 and make this 20. Okay, 15, 20. The acceleration is still 1.4. Okay, so let's make this 18 and 20. All right, so they're almost the same. 18 and 20, it's 0.52. And again, if you use that equation, this is what you will get. So this finishes off this chapter, ladies and gentlemen. It's the last problem. And so we are going to move on to chapter 5. All right, so let me just trying to line things up here.